Semiconductor manufacturing is, without a doubt, the most precise industrial process humanity has ever developed. But as our device geometries shrink further and further down into the nanometer scale, that margin for error, well, it's basically vanished. Welcome to this explainer, where we are going to uncover exactly how microscopic imperfections quietly accumulate across the manufacturing flow, ultimately disrupting your performance, your yield, and your reliability. Today, we're looking at why one incredibly tiny anomaly can become an absolutely massive problem for your fab.
So let's kick things off by asking a pretty critical question. When you're operating at nanometer scales in a modern fab, how much financial damage can just one single misplaced atom actually cause? Now, I know it sounds like a bit of an exaggeration, but one atom out of place can completely alter the electrical characteristics of a transistor. We really need to understand how these microscopic imperfections scale up to create some major macroeconomic headaches.
To get to the bottom of that, here is our agenda for today. First, the atomic scale challenge. Second, defects across manufacturing flow. Third, the heavy business toll. Fourth, opportunities in defect control. And finally, transforming challenges into innovation.
All right, let's dive right into Section 1, the atomic scale challenge.
You see, atomic scale defects don't just pop up at one isolated stage. They can originate anywhere, and the real issue is that they relentlessly compound through your entire fabrication flow. From the initial silicon crystal growth all the way down to packaging, there are warning signs. At literally every single step, material interactions, process conditions, or even ambient contamination can introduce structural irregularities. And the kicker? These defects don't just wash away in the next step. They physically build on top of each other, constantly magnifying the disruption to device performance and your final yield.
Let's break that journey down in Section 2, defects across the manufacturing flow.
We can look at this compounding problem chronologically, following the silicon wafer's journey. We start from a pure crystal ingot, move into surface prep and gate oxide formation, build up the device with thin films and etching, and finally finish up with back-end processing and packaging. Let's walk through exactly what goes wrong at the atomic level in each one of these phases.
The trouble actually starts incredibly early. Even during the initial silicon crystal growth, you risk oxygen contamination or crystal dislocations that just totally disturb the regular atomic arrangement of the silicon lattice. Then, when you move into wafer manufacturing, things like slicing, lapping, and chemical-mechanical polishing, those mechanical and chemical treatments introduce localized stress points. Even these impossibly tiny disruptions in the atomic structure act as leakage pads, and they severely weaken any subsequent thin film growth.
Moving down the line, even a routine RCA clean meant to remove particles can accidentally leave behind carbon contamination or hydroxyl groups, completely altering the chemical state of your silicon surface. But the real danger zone? That's gate oxide formation. Here, interface traps, charge trapping sites, and dangling bonds act as massive threats to your threshold voltage. And if we're talking about advanced architectures like FinFETs or gate-all-around transistors operating at extreme dimensions, their sensitivity to these interface defects is magnified. It's a straight line to higher leakage current and long-term reliability failures.
Next up, as we start building up those layers using chemical vapor deposition, PVD, or ALD, new risks jump into the mix. Poor nucleation introduces structural irregularities in grain boundaries. That leads directly to uneven electrical conductivity and dielectric breakdown. On top of that, energetic plasma etching literally breaks surface bonds, bringing in plasma-induced contamination. And when we use ion implantation for dopants, it actively causes lattice disorder and amorphization. Even after annealing, you're often left with residual defects that degrade performance.
Finally, we reach the back end, but honestly, the atomic scale damage doesn't stop there. In fact, defect accumulation sort of peaks right here. Interconnect formation, dielectric deposition, and more CMP processes create metallization irregularities. Later steps, like wafer backgrinding and dicing, actually physically damage the silicon bonds at the wafer edges, creating surface states and whole new leakage paths. Then, the packaging process itself introduces mechanical stress that interacts with all those underlying atomic defects we just tracked. It is, quite frankly, a cumulative nightmare for your reliability.
Which brings us to Section 3, the heavy business toll. Because in this industry, physics ultimately dictates finance.
The financial gravity of this situation absolutely cannot be overstated. These accumulating microscopic defects lead directly to severe, painful bottom-line impacts. The most immediate, of course, is reduced yield, chips failing electrical testing right there on the wafer. Beyond that,
Field failures lead to expensive warranty claims, product recalls, and huge reputational damage. And looking at the broader roadmap, these atomic-level contaminations are primary culprit behind those crippling delays we see in technology node transitions, especially as we try to shrink below 5 nanometers, where the margin for error is essentially zero.
Just think about the scale for a second. You are running billion-dollar fabrication facilities. The daily cost of operations is staggering. In an environment like that, a slight performance variability caused by one misplaced atom doesn't just mean a scrapped wafer. It means you can be locked out of incredibly lucrative, fast-moving markets. If your yield drops on advanced AI processors, automotive electronics, or next-generation memory, you're facing slower product launches and massive lost market opportunities that your competitors are going to gladly scoop up.
But let's pivot, because there's a flip side to this. Section 4. Opportunities and defect control.
You see, controlling these defects isn't just about playing defense or damage control. It's a massive value driver. When we compare the risks versus the rewards, eliminating just a tiny percentage of defects can generate millions of dollars in additional revenue per production line. But beyond just cost efficiency, mastering contamination control is the master key that unlocks the development of smaller, far more advanced semiconductor nodes. It is literally the fundamental enabler for the next huge wave of high-performance computing, mobile devices, and AI advancements.
So, how do we get there? Section 5. Transforming challenges into innovation.
The solution lies in leaning into advanced technologies. Industry leaders are deploying atomic-scale metrology and AI-driven process monitoring to get a real-time, highly detailed understanding of exactly how and where these defects occur. By combining that deep visibility with improved surface chemistry control and novel atomic-level purification solutions, fabs can finally stop guessing and start controlling. Doing so allows you to create far more reliable, energy-efficient devices, securing your position as a true leader in advanced semiconductor fabrication.
So, I want to leave you with a provocative thought to consider regarding the future of your own fabrication lines. As device geometries scale ever smaller, will you let a single, misplaced atom dictate your yield and your profitability? Or will you choose to master the atomic scale? The physical laws governing our industry aren't getting any easier, that's for sure, but the tools to conquer them are absolutely here.
If you're ready to transform these complex manufacturing challenges into a definitive growth opportunity, and for further information, please contact www.sysemi.com.